I'm also recording them to upload to YouTube, so people can watch it. We'll see if I can upload these tonight, because I have a bunch on this laptop that I haven't uploaded yet. That'll work. Cool. Okay, cool. So you guys are on homework 4. That's the one due tonight, right?
Yeah.
Okay. Yeah, you're good. You're good. So which problem are you working on from that?
So I tried attempting doing the first one on it.
Okay.
Sure. I mean, I'm still confused on it, honestly. You can take a look at how far I got, but I got to the K-maps, but I'm not sure if the rest before that is correct.
Okay. So remind me, what was the first problem again?
So the first problem was sequence detector.
Okay, yeah, that's the one.
Ones and zeros.
Right, that's the one we went over.
Yeah, so you
yesterday,
gave us a
or
different
last.
example.
Right.
And then I tried the actual one from the homework. And I did the state transition diagram.
Okay.
But I just don't know if it's correct or not.
I mean, yeah, I can take a look at it. Let's see. Reset state, you're detecting. Here, 6 0, go back to there. Here, 6 0, back there. Since if you are here, you're C1, still in the same state. If you are there, if you're here, 6 0. So let's go back. Here you get 1, yep. 0 go there, 1 go there. Okay, your diagram looks good, so the diagram's correct. State, this is probably correct. This one, this one. 0, this one, 0. Yeah, so your tables look good. So this all looks correct. I didn't look at this one. I'm just going to assume that you did the translations correctly, but everything looks correct.
Okay, cool.
So this looks good. Do you remember how to get to the schematic from there?
The schematic is it?
Yes.
I was going to get to the I was gonna
Oh,
do
the
a-
equations, yeah. You can do K-maps, yeah.
I don't think I need to for the first state bit.
Yeah,
Because
so-
it's single one. But I'm not sure if I even need to.
So yeah, if you remember, what kind of encoding are we doing for this one, for problem 1?
One?
Yeah, we're doing 1-hot encoding. And what was the strength of 1-hot encoding? Do you recall?
Strength?
Yeah, why would we use 1-hot encoding? It's just using up more bits, right? What's the benefit?
Only, how to explain it? But one thing is usually on. Yeah, only one thing is usually on.
Exactly one bit is always on, right? Well, what that means is if you see that a bit is on, what can you assume about the rest?
The rest
Yeah. So when you are doing your logic, you'll notice, like, for example, on this one, bit S4 is on, right? So you don't need to put the rest of these because
Okay.
since that's on, you know those are off.
And I was comparing it with the example you gave us the other time.
And that's why it
And
looks
I
a
was
little
like,
different.
okay, it's a lot less. I don't think I need to include this as well. So we just have S4 is just the only thing that's
Exactly,
on.
yeah.
Okay.
And maybe for this one, for example, for this lime green color,
And that'd be the only
that'd only be
state bit that'd
S3,
be-
right? And then the rest you don't have to include in the equation. Yep. So that's the only difference, but what you're doing is correct so far, and at this point, you wouldn't even need a K-map
Right.
because it's 1 bit here and then 1 bit here. So that's 2-bit inputs. The equation's not going to be too bad. You don't really need a K-map for that. Sound good?
Yeah, the only one I guess would be
Maybe that.
the green. Yes.
And the green one, maybe.
And the green. So it'd be 3.
So you could do K-maps for those totally, and it would be a 2-input K-map. So it would just be, it would just be a square, really.
Yeah.
A little square. Okay. So someone joined in. Oh right, you joined in the Discord. Go ahead and talk. I'm gonna see if my audio is working again this time. Oh, it's not. What did you fix last time? What was wrong with my audio?
So usually what happens is that, I guess Discord, you can set a default. It'll select the speaker to be selected by the default. I think that's a speaker as well.
Yeah.
So you have to select the actual speaker on the computer.
So in the voice settings?
So the input settings, we're gonna make
That one's correct because that one's this microphone.
And we have your speaker set, so that's set. So it should be working. Do you want me to hop on to see if I can hear you?
Well, like someone came in and I can't hear them, but I know they can hear me because I told them to.
Say if you can hear me.
Yeah, and they responded. I could see their thing lighting
the
up.
next thing you would do is you would check the actual Windows settings. So
That's a good point. Let me check that. That might be. Oh yeah, that's it. That's exactly what it is. Thank you. All right, can you talk again? I think that might have fixed it.
Hello?
Oh, no, that didn't.
Hello, hello?
God damn it. Wait, there we go. Okay, I actually have audio coming out. I think it's good. Could you speak one more time?
Hello, testing?
There we go. Okay. All right, yeah. It was. I don't know why my Windows defaults to this.
sometimes you can actually set default to go to.
Oh, that's right.
Stuff like that, but I'm not sure if you want to do that after.
I'll probably just do that after. Anyways, so you came on Discord. Did you have any questions for me in regards to homework 4?
Yes. So what I see from number 5, it says that we need to detect the user inputs to sequence 593. So to find those states, I'm assuming we would need to convert those into bits first?
Yeah, so that's the basic idea. You need to encode the numbers, the decimal numbers, as binary bits, right? How many bits do you think you'd need?
Like I would assume like it needs to take into account the highest decimal value, which is 9.
Right.
So that would just be
How many bits do you need to represent 9?
Technically 3 bits, right? To the 8.
Well, let's see.
No.
What's the biggest number with 3 bits? Let's try it out.
3 bits, 2, 4, 8.
This number
that's
is... What's this number?
1, 2, and 4. Oh yeah, that's 7.
That's 7, right? So we need more bits. In fact, to represent 9 in binary, we need 4 bits, and it's like this. So the zeros place has a 1 in it, and the 2 to the thirds place has a 1 in it as well, so that's worth 8. And then when you add those up together, you get 9.
Yes.
So you need 4 bits to represent any of those numbers. What I will say, though, is that to simplify the process for you when you actually draw out pretty much everything until you get to the schematics, instead of writing stuff in bits like this, write it in terms of the decimal number. So, for example, if you're looking for an input signal
Wait,
5,
sorry, you're muted?
Am I muted?
I can hear you. I can hear him.
You might
Yeah, I can
have
hear him fine.
my...
Oh, shoot.
my,
Must be something with
that's
mine.
right, from last time. I told you to mute it because there was audio coming through.
But I can hear you. I just can't hear him.
Could you tell her to click on my character icon and increase the
Okay, yeah.
volume?
Click on Victor's character icon, and you should be able to see that the slide is at 0.
Oh, yeah, it says muted by you. Sorry.
Yeah.
Okay.
Cool. Can you hear me now?
Turn this off. I'm so sorry. I'm like.
I think you can just click the thing that says muted. I believe.
So did you have any questions with the schematic stuff or anything? Or like the
For
simplification?
this,
I'm trying to click it and it still says muted by you. I'll figure it out. If you guys want to continue, sorry, I'll mute myself, figure this out.
making schematics and stuff like that.
If you want, you can also stream it.
So I just saw homework 5. The first one.
Looking a little rough.
It says it should detect patterns. 0, 1, so 2.
Yeah, 2 separate ones, right?
Yeah.
So you're detecting 2 separate patterns. What do you think you're gonna need?
We need 2 separate episodes.
That's probably the best way to do it. You could do it with one, but it'd just be kind of hard to think about all the different possibilities. Do 2 FSMs, yeah. And then at the end, if the first FSM tells you you detected a sequence, or the second FSM tells you you detected a sequence, what does that mean? Yeah, you assert the output. So if this guy asserts true, or that guy asserts true, then you assert true. What gate is that? And as a hint, I said the word.
I didn't hear you actually.
No worries. So if this FSM asserts it, or if the other one asserts it, or gate, yeah. So at the end, you just take the outputs of both FSMs, or them, and you're done. Let me go ahead. I'm going to share my screen really quickly,
Okay.
and that way Shauna can see how to turn up the volume.
Oh, I got it.
Oh, you
I
got
can
it?
hear you.
Oh, you got it.
Yeah, thank you.
All right, good.
I see you're working on number 2 for the homework 4.
Yeah, the
Is
one. I think homework 2 is the number one where we're doing detecting
Yes.
593, right?
Yes. Yes. Okay, perfect. Thank you.
Okay. So I think what I'll do is continue talking about what I was referring to before. So yeah, you need a total of 4 bits to represent these numbers, because the highest number you have to account for is 9, and to do 9 in binary, you need at least 4 bits. So we do need 4 bits of information coming in as an input. So normally in these FSMs, you're used to receiving like a 1-bit input, but for this problem, you have not just 1, but 4 bits, right? 1 for each place value of your number. And so taking stock of all our inputs and outputs for this FSM, we have the 4-bit input of whatever the number is from the garage door keypad. So I guess I'll call it N to represent number. And it is a 4-bit signal, so I put 3:0. For inputs besides this one and then the standard ones, clock and reset, that's all of your inputs. There aren't any other inputs coming in. And then for the outputs that are detailed, it's just saying, did you detect the correct code? So I think it was G was the name of that signal, so that's an output. And the way this is going to work is whenever someone presses a keypad, what's going to happen is essentially the 4 wires that make up those bits are going to light up with the number that they pressed. So if they press 9, the first bit is going to be 1, and then a 0, and then a 0, and then a 1. And those are all going to come at the same time. And so what I recommend doing for the FSM is not putting the binary bits as the transitions. So you're used to putting like a 0 or a 1 for the transition, or like A bar or A for transition. But for the sake of simplicity and making this easier for you guys, what I recommend doing is on transitions, just put like the actual number that it would correspond to. So if we need to read in a 5, I would put a 5 on the transition line. And then maybe for like, if it's anything except 5, you could do something like 5 bar. Which, while not technically correct notation, it is something that helps you understand what it means, right? It just means anything except 5, so not 5. And that's how I recommend you guys label your FSM. So what I'll do is I'm going to write down the sequence that we have, which is 593, and I'm not going to do that one. I'm going to do a different one. I'm probably going to do, let's do 721. So that you guys can get an idea for how to do this problem. and then still be able to do it yourselves afterwards. But it's almost the same process, just a few different numbers. Okay. So, what is the first thing we do when we have an FSM we're trying to make? It's the very first thing.
Find our inputs and outputs.
We need to figure out our inputs and outputs. So we just talked about those, right? So the inputs, clock reset, the basic ones, but also the 4-bit input of the number, so N3:0, and then our outputs, which are just G, the garage doors opened. So that's also like the black box step, where you draw just a box with the wires coming in, the wires coming out. So that's all step 1. What's the next step? What do we do next?
We need to draw our transition table, like with the circles.
Yeah, that's right. We need to draw our state transition diagram. That's right. So, yeah, it doesn't matter what you call it. Not really. I don't think you're going to be quizzed on what the name of the transition table is. As long as you can do it, that's what matters. So why don't I start with the easiest state? I'm going to do the first state, which is the reset state. Where's this? It's over here. Okay, so I put on the reset state up in the top, and I guess we'll start with the first few transitions. So what are my transitions going to be from the state?
Whether it goes to 7, I believe, right?
Yeah, whether it goes to 7 or not to 7. So I guess I'll draw the first arrow to the next state. All right, so that's my next state. That's S7. And how do I get to that state?
When 7 is inputted.
Yeah, when 7 is inputted, that's right. So ordinarily on that transition, you'd put like a binary bit, like A or A bar. But in this case, I'm just putting the number 7 just to remember for myself that just corresponds to the binary number 7. When you receive that as an input, that's what you're doing.
Sorry.
Go for it.
Would we be able to do the same thing? That wouldn't that wouldn't deduct points for us, right? As it's just like a table to like.
This is the better
help
way.
us.
I mean, this is probably, I haven't looked at it at the solution guide, but this is probably how it's written on the solution guide. This is typically how you would do it.
Mm-hmm. Okay, thank you.
Yep. So now that we have the quote-unquote correct input from the state of the FSM, what other transitions come from the reset state?
It doesn't detect 7.
If it does not detect 7, and where would we go?
We go back to the reset state.
That's right. So again, I'm not using necessarily standard notation, just notation that would make sense to us, not 7. Okay. So now what we're going to do is I'm going to have you guys think about what the next one is going to be, what the next 2 transitions are going to be, or the next few transitions are going to be from that state. So give it a try and write them out, and then whenever someone's done, you can let me know, and we'll go through them.
for state 2,
Okay.
I detected that if state 7 and then the input is 2, then we'll go to state 2. However,
that is correct. Yes.
okay, and so if it's, however, if the input is anything but 7, then it will have to restart to SR, right?
Yeah. So if it's not 2 and it's not 7, it goes to reset.
Mhm.
And what you're alluding to here is one other transition, right?
Yes, where if the input is 7, then it has to go back to state 7.
That's exactly correct. Yes. So just like you said, if we get a 2, we move on because we detected the correct sequence. If we get a 7, so the next one, according to the directions, it's allowable for the code to be something like. This is an accepted input according to the description of the homework. So we have to account for that here and say if we get another 7, then we stay in state 7. And last but not least, if it's not 2 and it's not a 7, then we have to go back to the reset state. So I'm going to write that just like I would if they were binary bits. So just like that, not 7 and not 2. Okay, so now that we've finished up the reset state and we've finished up state 7, we're now on to state 7.2, and I'll let you guys finish up the FSM. And I'm going to go ahead and start writing the transition table, or the next state table over on the right-hand side for us to be filling out in a second. So I'll let you guys go and finish up the rest of the FSM. Alright, so it's fine if you guys haven't finished up yet, but I was going to ask Shauna, do you have the transitions from this node finished yet or not yet?
I do.
Okay, cool. So what do you got?
So I have, you're gonna, if it's a 1, you're gonna go to the next state, which is 721. I think 721 was our original one, right?
Yes, that's right, 721.
Okay. Yeah, so you're gonna move 721 and then output G in that circle as well. And then I have, if it equals 7, we're gonna go back a state
Yep.
to S7. Okay,
Yep.
good. And then I have, if it's not 7 and if it's not 1, go back to SR.
That sounds exactly right to me, yep.
Okay, phew, good.
Alright. Javier, did you finish up the last one?
No, I didn't.
That's all right. We can work through it though.
All right.
So let's start with this. What are some possible inputs that you think might make us go to like one of these ones instead of reset?
If we got 7 again. we can
Okay,
go-
so if we got 7, yeah, that's a great idea. So if we got 7 again, from the output state we go back to S7 because we got another 7. Okay, and then are there any other special ways we can go? Like, can we get to this one somehow?
Yeah, we got 7.
So if we have, because we just got 7 to 1.
Yeah.
If I receive a 7, that can go to state 7 because then this can be a 7 to 1
So it
sequence
covers the
again.
rest of us.
Can we ever get back to this one from yet?
I mean, I'm assuming the way that, because we're typing in a keypad, right? I'm assuming that it's like one sequence every time.
Yep.
You can't.
That's part of the
at same
assumptions, I
time,
think.
Yeah.
Yep.
You can't put it at the same time, so I mean, once you get everything again, I mean, it's not 7, then go back to SR.
And that's exactly right. There's no way to go straight from here back to here. You'd have to first go to S7 and then go to state 72. So yeah, in any other case, so if it's not 7, we go back to reset. All right. And so now we finished up our FSM. It's a little bit less crowded than the one we had for the last office hours. Last one was, I think it was like 6 states compared to this one having 4, so not too bad. And then just as a review question, actually, is this encoding supposed to be 1 hot or?
Alright. Yeah.
Okay, so we're doing this as 1 hot. If we weren't doing 1 hot, how many bits would we need to use if we were doing just binary encoding? And why?
Three bits, right?
Sorry, how many?
I think 3 bits.
All right,
'Cause
so
we
let's
have
see. So what's your explanation for it?
So we have 4 states,
Yeah, that's right. Yep.
and so we would need to go up to 4. And so in binary, that would have to be 3 bits.
Very close, but
Okay.
you didn't count the number 0. Because if you count starting from 0, you get 0, 1, 2, 3. That was 4 numbers there. So you have 1 through 3, that's 3 numbers, and then 0 is your 4th.
So I thought that would be for the 1 hot state.
Well, so you can think about it like this. So we have binary encoding. And binary just means we can use all of the numbers up to however many bits we have. So use it as efficiently as possible, use all of them. And so that's what I'm going to do. Oh, that's nice. And so this definitely isn't a 1 hot encoding. This is a binary encoding, but that's fine. We don't need to be 1 hot. And there are 4 distinct states. We have the number 0, the number 1, the number 2, and the number 3. So there are 4 states we can represent with just 2 bits. So we don't need 3.
I see. I see. Thank you. Yes,
for
I
sure.
totally missed the 0 for some reason.
No worries. Okay. So if we were doing this with binary encoding, we would only need 2 state bits. So that means our register would only need to be able to hold, well, 2 bits. Versus if we were doing this with 1 hot, which we are, we need 4 bits, 1 for each individual state. All right. So over on the, well, I guess for you guys it would be right. Over on the right-hand side of the board, I have part of the next state table written up. And I have it written up with a few of the states. So I just filled out the bubbles for SR and S7. So I'm going to go ahead and finish filling out the rest. And then we can talk about what the next state, what the output is going to be. Alright. So I finished writing up the last few rows. I haven't written the outputs because I want you guys to fill that in on your papers. But, while I'm talking, you can fill that out. You'll notice that I filled in exactly as I labeled on the transition diagram, the same on my input. I didn't list the bits individually because these encodings, while we could write them in a table, it's kind of like if you were to write the state 721 as its bit encoding. You can do it, yeah. And in terms of when you're drawing the schematic, you'll need to do that eventually. But for the sake of simplicity and understanding, it's a lot easier to write that, and it's faster too. So we'll stick with that for now until we actually get to the schematic, and we can replace them if we need to. So we have gone through a few steps. We have firstly drawn the black box diagram and talked about the inputs and outputs. The second thing we did was we figured out our FSM diagram. That's this one over here. Then the next thing we did was we did our next state table. I skipped one step. Do you guys remember what that step is? Though it's kind of interchangeable. It doesn't matter what order you do it in.
Did you, I usually do our state encoding table, like
That's right,
third.
Yeah, you can do state encoding like right after this. You can do it after the next state table. You can do it after the output table. Those three are kind of interchangeable. It doesn't really matter what order you do them in. All I'll say is that if you don't want to rewrite this with binary zeros, you want to just start with binary zeros, you got to do your encodings first. So yeah, I'll go ahead and write that off to the side. So, I've written up the encoding table, and I have gone out of my way to make a mistake. So, I want anyone who is looking at the encoding table, over up here, to tell me if they can spot the mistake and what it is.
Or, because you're doing like one hot encoding, right? Wouldn't SR need to be 0001?
Exactly, because by definition, one hot needs exactly one of the bits to be high. And in that first row, I have no bits high, so that's not the correct encoding. Very well done. Okay, so I finished up my state encoding table. Now, have you guys finished up your next state table? And it's fine if not, but I'm going to start writing them in.
I'm not quite done, but you can definitely keep going. Because it's kind of like, it's a little hard to see on this end, so like I'm going
Let me
slowly.
see. I might be able to scoot this over a bit, make it a little easier.
Yeah, it's like the ones and the sevens I'm having trouble seeing, but that's a little bit better.
It is a little rough to see them. Okay. All right, so I'm going to start writing some stuff in. Actually, I'll do this. I'm going to ask for this first row, which is when you're in state SR and you receive a 7 as an input. What should I put for the output? Or with the next state?
State 7.
0001. Oh, sorry, Good Noodle. Sorry.
Oh, no, you're fine, Shanna.
So which state? So which state did you guys say we're going to?
Zero, zero, zero. Oh, sorry. No, we're going to 0010.
Yeah, that's right. So we're going to 0010 or state S7. So I guess I'll write it, for the sake of just time, I'm going to write it as S7, but you guys on your papers can write 0010. Then what about for this next one where we're in state, the reset state, but we receive not 7? Where do we go?
Then we'll go to 0001.
Yeah, we go back to the reset. Okay, I'm going to throw one more in here. I'm going to say we're in state S72, and we don't get a 1 and we don't get a 7, where would we go?
SR.
Yeah, that's right. Okay, I'm going to fill in the rest of this while you guys do as well. So I finished writing in all of the next states for the next state table, and then the next step we're going to do is we're going to move on to the output table. So for the output table, what are going to be the things that go in my truth table? It's okay to be wrong. You can speak up, I promise.
Place the current state where G that's a certain.
Yeah, that's exactly right. You would put the current state that you're in, because the output depends on the current state. And because this is a more FSM, the current state is the only thing it depends on. So your inputs are just the current state, and your output is just G. So those are the only things we have for this truth table. All right. And then going through the possibilities, we know that we only assert G in the final state. So according to our encodings, that occurs when S3 is on. So I'm going to go and write that in. And in the other three cases, it doesn't matter what we get, we're always going to have 0 outputted for G. And so given this, what would be the equation for G? What would we write?
G equals S3.
That's exactly right, yeah. So this is state bit 3, and so our output equation is just G is true when you're on state 3, in state bit 3. Okay. Now we can go ahead and do a similar derivation for the next state equations. So we've moved on past the tables, and now we're deriving the Boolean equations, and then once we get the equations, we can move on to drawing the final schematic. So again, like I mentioned earlier, when we get to the schematic, we're going to have to write these as bits, the 5 and the 7 and whatnot. But for the sake of simplicity and for writing, I'm going to write the next state equations in terms of 5 and 7 and whatnot. And then we can translate it to the schematic as needed.
A quick question, though.
Yep.
But for the homework, we do, like, I did it in the, like, okay, maybe I'll let you finish. I'm just...
you did it in binary, right? For your...
Yeah, I ended up with like N3 or N2 bar or N1 or N0 bar. Yep. And S0, like all of that stuff. Like we would have to do that on the homework, yeah?
Nope.
Or can we keep it simplified?
So here's what I'll say. As long as your schematics are correct, the way you notate this, if you notate it this way, it's correct. It's going to be correct. And I'm pretty sure on the answer solutions, this is actually how it's going to be notated. Possibly showing both tables with this and the one you were mentioning with the full equation of, this bar or that bar or that. The main point here, just in general, is when you are designing an FSM, go with what makes sense to you for this kind of notation. Don't write everything in a binary if it is not if it doesn't lead itself into being written in binary. If it makes more sense to write it as a decimal number, write it as a decimal. And when you get to the actual schematic, then you can go ahead and replace stuff with bits, because it's going to be a lot easier to think about, oh yeah, when I'm in state 72 and I get a 1, I go to state 721, as opposed to, well, if my state is 0100 and I get a 0001, then I go to state 100. That's just, firstly, it's a mouthful to even say, and secondly, it's a lot harder to think about. So that's why I recommend doing it this way, because it's more intuitive and it makes more sense with the way that we name the states and the way that we process the information in our heads, as opposed to just bits. So I would just go with this stuff.
I would have definitely saved a lot of time if I had just gone with that.
Yeah, it can be quite a pain to do it
a
all
lot.
in binary.
Very confusing what I have
Yes.
written. So, okay, that's good to know. Thank you.
Yeah, for sure. So what I'm going to do, like I said, I'm going to write the equations, and then we're going to talk about how to transform these equations that are written in kind of the weird notation with the 7s and 5s into an actual schematic. But I'll start with the equations. So I'm trying to think of what an easy one would be. So I'll do state 721. Specifically, I'm going to write the output equation for S bit 3. The reason why I'm writing it for the next state of 3 is simply because there's only one case we actually get there. That's right here, S721. There's only one possibility for that one. And that occurs when we're in state 7, S72, and we get a 1 as an input. So I'm going to actually go ahead and write that in. So I have state 72. And how would I actually write this in my equation? It would just be S2 and 1, that's right. So a few things. This is going to look weird. This is the decimal number 1, not the binary bit 1, so keep that in mind. This is a digit, not a this is a decimal digit, not a binary bit. And the second thing is, because we're doing one-hot encoding, when we see that this bit is on, we know automatically that the rest are off. So if S2 is on, we don't have to also write S3 off, S1 off, S0 off. That's not necessary, because we know by the way we did our encodings, we don't need to include those. Okay, so now I'm going to let you guys start writing the equations. I'm going to write a few of them down, but I'll let you guys go and do it on your paper for some practice. Okay, so I'm going to go ahead and write the equation for S2, for the next state of S2. So for that one, we're going to look for all the spots where we have our output is 72. So I think that's just on this one. That's the only spot where we have state 72 as an output. That occurs when state 7 is the current state we're in, and we receive a 2 as the input. So state 7, that corresponds to S bit 1 here. So I'd say S1. And we've received a 2. Now for the last two states, we have 4 possibilities for each. So we have state 7 occurring 4 times and the reset state occurring 4 times. So we should expect 4 individual terms for each of these. And I'll go and start writing them out, and then you guys can compare with your results. So I've used up most of my board space, but I've written down all the equations for these. So like I mentioned before, each of the final two states only have one way of possibly getting to them. For state 721, it's when you get a 1 from state 72. And for state 72, it's only if you're in state 7 and you receive a 2. So that corresponds to these two equations here. And then the two starting nodes, the two starting states, SR and S7, each have 4 ways of getting to them. For S7, that's the easiest way to think about it. Whenever you're in any of the states and you receive a 7 as an input, you go to state 7, no matter what. And then for the second one, for the reset state, there's a few different ways to get to it. If you are starting in the reset state and you don't get a 7, then you go to the reset state. That's this one. If you're in the first state, so state 7, S7, and you get a not a 7 and not a 2, then you go to reset. And then it continues on. If you're in state, the second, the S2 bit state, state 72, and you get not a 7 and not a 1, you go back to reset. And then finally, if you are in the very last state, that's S721, which corresponds to state bit 3, and you don't get a 7, then you go back to the reset. Anyone have any questions or concerns? All right, I'll take that as a no. And now that we've written out the output and next state equations, all that's left for us to do is to figure out how to do this schematic, because we've been putting off this how do you encode a 5, how do you encode a 7 business for quite a while, and we're going to actually do it now. So here's what we're going to do. I'm going to write out each of these numbers in binary, so starting with 7 and then 2 and then 1. So in binary, the number 7 is represented as so. So 0 on the most significant bit, followed by a bunch of 1s. 2 is represented with 2 zeros, a 1, then a 0. And then 1 with 3 zeros, followed by a 1. So now we need to think about how we're going to use these signals in our actual schematic. Because remember, the way this is actually encoded is we have 4 wires coming in, sending bits to us. And so this is kind of the way it's split up, right? We have these bits and 3 and 2 and 1 and 0. And so the easiest way to do this kind of goes back to when we draw schematics. You know how sometimes if I'm doing like the input A, I do a little offshoot with an inverter just in case I need an A bar somewhere, just in case I want to pick it off and I don't want to have to add an inverter later in the logic. We're going to kind of do a similar thing here, except with 7, 2, and 1. So here's what I'm going to do. I'm going to say, I'm going to call a signal, I guess I'll call it is 7. I think that's what the naming convention that you'd see in the answer key is going to be. So I'll go along with that. So this signal is going to be true if we received 7 as an input. When can I say we've received 7 as an input? When is 7 the input?
When n sub 2, n sub 1, and n sub 0 are all 1s.
And n3 is 0.
0, okay.
Yep. This is the gate, which corresponds to us receiving a 7. And so on my schematic, I can put this gate. And so now that I've drawn this gate out, I can use this signal anywhere I want in my entire schematic. and this represents that you've received a 7. It's a similar process for the rest. So for 2, you would just change the way the inverters orders. For 1, again, you just change where the inverters are. And I'll talk about doing not 7 with you guys, and then I'll let you guys figure out how to do the rest of the gates. And from there, the schematic should be exactly identical to the way we did it before, except instead of having, N3, N2, N1, N0, instead of using those bits, we're going to be using this as inputs for our schematic, just because we can bundle them up into this nice package that we actually utilize in our truth tables. And that's why we left it in this format, because now we can express the signals in that format and make it easier for us. So how would I say not 7? How would I do that?
Can you just do like a little circle like after the and portion? Yeah.
And that's exactly correct, right? We could have, if we wanted to, said, okay, well, let's look at this and look at the equation that makes it up. And then negate it. And then do some De Morgans and get down to simplifying. And you'd end up with an OR gate and some inverters. Or we can take this already existing hardware, negate it, and we're done. So I'd go with the second one, since we already have this AND gate. No need to make an entirely new signal for not 7, when we can just put an inverter after the is 7 signal. And that's how the rest of them are going to go. It's going to be something like this with an inverter after, if you need the inverted signal. Though I will say that for this particular problem, you don't. Actually, no, you do need all of them inverted. So you need 7, you need 2, and you need not 7, not 2, not 1. But I don't think you need the signal for is 1. So you can just do is not 1 if you want, or you can do is 1 and invert it, up to you guys. But essentially what's going to happen now is, after you draw each of those gates so that you show on your paper that you have the signal, now you can use it freely in your schematic wherever you want. So for example, if I was doing, let's say, S bit next state bit 3, instead of having to write out this whole gate right there, I can use the is 1 signal. This, here I'm pointing at is 7, but for that one it's is 1. Yeah, that's right. Okay, and so now you'll see over here we have just a single AND gate that connects if we're in state, if state bit S2 is on, and we have a 1 as the input. And this works. This is completely correct. You would just have to show this diagram for is 1 instead of is 7 off to the side. And that's how the entire design is going to go. You're going to have these, and then you're going to have your outputs. And remember that according to our output table, G is equal to S3. So I can just label that Y or G as well. And that's pretty much the whole design. The only extra thing I haven't shown you, like I said, is the other versions of this for 1 and for 2. And then the extra hardware you'd need for the other states. But now that I've kind of run through how we handle these cases where we have these bundles of bits, well, you can, just like we abstracted the details away of how we created the sequence in the truth table, we're also abstracting the details away by creating this signal, and now we can use the signal anywhere we want. And that's a big part of any kind of design you do, digital or analog, being able to abstract details away and kind of simplify stuff. You don't always have to dive into the deepest depths just to, make two numbers add together. You don't have to look into each individual gate. You have bigger pieces of hardware that are composed of smaller gates. And that's the point of this, kind of teaching that abstraction detail, as well as hierarchy and modularity, which I think you guys might have went over in 100. I don't remember if you guys went over that, if you didn't take Harris. But that's kind of the go over for this problem. So, any questions with what I've covered so far? Any comments? Or grievances, perhaps? None? Okay. Okay, well, if everyone is comfortable with this question, then you all should be good to finish up the same question that's on your homework tonight as well. Because it is due tonight, right?
Yeah.
Okay.
Yes.
So, exactly the same process, just a few different numbers. It's gonna look identical to you, really. Just the 5s and the 8s and the 3s are switched around, and it's gonna be basically the same thing. So, you won't have to worry about it too much. Were there any other questions you guys wanted to go over in the few minutes we had left? Because I could go over another question, or I guess I could finish this one up, but I don't imagine you guys need that much help finishing it up. If you do, though, I can.
Wait, sorry, can you just move a little bit to your... Okay, so we are drawing the bundles like vertically, and then the wires are gonna go horizontally into the next like AND gate.
You can do it however you want. I mean, probably the way that... I just did this to draw one, but probably the way you'd want to do it is the way I did the schematic last time, which would look with vertical bars.
Yes, okay. That's what I was thinking.
And then you'd pick them off. And obviously you need more room than I gave myself here, but that's the typical way to do it. You can do it the way I just drew it, though, as well. That works, too. It doesn't really matter. What else? Oh, yeah. Last thing, if you are going to do it with the lines up and down like this, you could also just have this schematic up top here with this wire leading to it to make it very obvious what you mean when you say is7. You're referring to this signal. So that's another thing you can do as well. It doesn't really matter, though. As long as you have that signal labeled somewhere, then the reader or the grader should know that you're using that signal for the one that we have labeled up here. Well, I erased it, but the one that was here. All right. Any other questions? Okay. Well, we don't have a lot of time to go over like a full problem. If anyone has like minor questions or like small things that they don't understand, or maybe something from lecture that you guys didn't understand from today, we can talk about that too. Okay. How many questions are on homework 4? Like 3, right? Or is it 4?
It's just 2, and we went in homework 4?
Yeah. I haven't looked at it. I like went over the problems, but I haven't looked at the whole page.
That's the one due tonight, right?
Mm-hmm.
Because I know there's the sequence, and then there's the like the 11010 sequence, and then there's this one.
Garage code, yeah.
We did them both.
Oh, is that it then?
Yes.
Yeah.
Oh, no wonder you guys didn't have questions. Okay, that makes sense. I was like, aren't there more questions on the homework? Okay, that makes sense. It looks like someone just came into the Discord. Did you have any questions for me? Because we only have like 5 minutes left, so we can like briefly talk about something. But
just checking in, seeing if maybe my questions can be answered just by looking at this, at the layout. So
I mean, you can, but the thing is,
yeah.
I've been asked by Dr. Harris to not go over the exact problems. So this one's very similar.
Yeah.
But a few different numbers.
Okay.
So I guess while we're here for the last few minutes, quick recap on 4 FSMs, what you're supposed to do. First step, you want to do your black box diagram. You can do that visually by writing it on a piece of paper, or we can talk about it verbally. So we can figure out what our inputs are, what our outputs are, and what we want the circuit to do, just as like a general idea. The next step is to actually write out your FSM diagram. So that's figuring out, hey, we're starting in our reset. What do we want to happen? Where do we want to go? Draw on all our reset, draw on all our transitions, account for all the cases, and that will be your state transition diagram. After that, you have to make your tables. So for a more FSM, you have 3 tables. You have your state encoding table, you have your output table, and your next state table. For Mealy, it's almost identical. You have the encoded states table, and then the output and the next state are just one table, so it's only two. So after you get your tables done, then from your tables you derive your equations. So you have your next state equations, and then you also have your output equation. You take those, and you then implement them in hardware with a schematic, applying any form of modularity or hierarchy and abstraction where you need. So for example, like we said, if we're using a signal that says, hey, this is the number 2, then I can make a gate for that and then use this anywhere I want. Just like how in the previous office hours, I would say, okay, well, I'm going to draw a single line representing this, and then I can use this signal anywhere in my schematic that I want. I can do that with a signal that I make too, not just inputs and outputs. So that makes it a little easier to not have to draw this every time you need the input for it's a 7. Because in standard hardware, you wouldn't recreate that hardware. You just take the same hardware and run a wire from it to to wherever you need it multiple times. Okay, and I think that is, yeah, that's the entire process. So anyone have any questions for me? Because I know someone else just joined in. We only have about 3 minutes left in the office hours. No questions? Okay. What I'm trying to do, I'm going to try and do this tonight, is I have been recording some of the office hours. So I'll be posting those. I'll be uploading those to, I don't know how to upload them to Canvas. I'm going to be uploading them to YouTube just because it's probably going to be easier for me. I can talk with Dr. Harris later about maybe uploading them to Canvas, but they'll be more permanent on YouTube anyways. So I'll try and upload those tonight. If any of you remember and I have not uploaded them by or I have not started to upload them and send you guys a link by I want to say 8:30, you can send me a DM and I'll get on that. But if there aren't any questions, I'm going to be ending office hours because we have about 2 minutes left, and that's not enough time to go through a whole problem. I could answer small side questions though if anyone does have any.
Thank you so much.
Yeah, of course. My pleasure.
Thank you.
You're very welcome.